Okay, we're going to start Chapter 2 here today. This is Section 2.1. We're going to be discussing in this section different ways of describing the location that a piece of data is within a distribution. Okay, we're also going to be looking at how transforming a set of data changes measures of location, center, spread, things like that. Okay, all right, so let's start with one measure of location. And that is a percentile, okay? A percentile measures the position that a piece of data is, okay? It says here, one way to describe the location of a value in a distribution is to tell what percent of the observations are less than it. Okay. Please note here, though, that the percent correct, say, on a test is absolutely not the same thing as what a percentile is. These sometimes easily get confused with each other. A percentile means location as compared to others in the data set. Okay, so when we say that they're in, say, the 10th percentile or the pth percentile, this is the value where p% of the observations fall underneath or are less than it. So let's look at an example here. We have Jenny. It says that she earned a score of an 86 on her test. The question is, how did she perform relative to the rest of the class, and what percentile is she ranked in? Okay, you can see what they gave us here is a stem and leaf plot. Okay, here's our key. So we see that an 8 with a bar and a 6 represents a score of 86, which would be Jenny's score here. Okay, that means Jenny's score, I kind of have it bolded a little bit, okay, is right there, the 86. Okay, if you were to count the number of leaves over here, the number of digits, we would discover that there are 25 students in the class. Okay, 25 students in the class, okay? And so what we're going to do is we're going to figure out, okay, Jenny's score is greater than how many of these students' scores, okay? Looks like Jenny's score was greater than if we were to add up all these students here. Her score is greater than 21 of the 25 students. So if we were to take 21 divided by 25, we would roughly get 84%. So that means she is in the 84th percentile. Okay. A lot of times percentiles are used to interpret SAT scores and things like that. Here's another extension here of this question. It says, what are the percentiles for each of the following students? So let's say Norman is the guy that earned a 72. Okay, so what we would want to do is out of the 25 students, we would want to count up, remember, percentile is how many were less than that person. Well, there was only one other student in this class who scored less than a 72. That's this person that got the 67. So 1 divided by 25, that roughly is going to work out to the 4th percentile. Okay, then we have Katie. Katie scored a 93. Okay, she scored a 93. So there were 24 of the 25 students who were underneath her. So that means we've got her falling in the 96th percentile. And then it says 2 students who earned a score of 80%. Okay, you can see how that's duplicated right here. There were 2 students who scored that. Okay, so we're going to count the number of students that are underneath that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, there were 12 out of the 25 who scored less than an 80%. That puts both of those students in the 48th percentile. So you kind of get the idea that a percentile is giving you your location as you compare to others. Okay, as you compare to others. Okay, another measure of location that kind of works in percentiles is something called a cumulative relative frequency graph. Okay, and this displays the cumulative frequencies in the form of a line graph, and this graph is made up actually of percentiles. Okay, so over here you can see we have basically this is a histogram here. Okay, this is a histogram, and this is converted into what we call a relative frequency graph. Okay, or I'm sorry, a cumulative frequency graph. And I'm going to just highlight the word cumulative here. What I want you to take note of is how this accumulates, okay, as it climbs. Okay, now look at what the left side represents. Okay, this is representing, when it throws in the word relative here, this is climbing up to 100%. So when you get all the way to the end of the graph, you've now accounted for 100% of the data. Okay, something that's definitely worth noting is that the steepest section of this graph indicates where the frequency is increasing the quickest. Okay, like it looks like the steepest section of this graph might be that section right there, and that looks like maybe just to the left of a score of 15, or kind of in the middle of a score of 15. And look up here at the histogram. The histogram, that coincides with this bar right here that did have the steepest section the most, and so that's indicated with the steepest slope here. Okay, so let's look at a problem that's kind of similar to this here. Okay, we are asked, it says here is a cumulative relative frequency graph showing the distribution of the median household income for the 50 states and the District of Columbia. Okay, so our x-axis is the median household income for all the states of the District of Columbia, and the y-axis is the percentages. Once again, notice how it always ends at 100%. Okay, now it says California has a median household income of $57,445. What percentile is that? Okay, so what you're going to do is you are going to come along the x-axis and roughly estimate where this 57,445 is. Okay, so we're going to say roughly maybe that's right about there. Okay, and then I want to figure out, well, where is that on the y-axis? Okay, where that point is. I'm interested in like this point right here. Okay, so then I'm going to drag this on over, to the y-axis. Okay, and it looks like that it's landing at 80%. Okay, now here's what this means. California, which has a median income of $57,445, is at the 80th percentile. All these other states that came before it had smaller median household incomes than California's, so it has a higher median household income than 80% of the other states. Okay, so I'm going to go ahead and write down here that California is the 80th percentile. Okay, that's the percentile. And we're going to say California's median household income is greater than 80% of the other states and the District of Columbia. I'm going to abbreviate there. Okay, that is the interpretation for that. Okay, let's look at example B here. It says, what is the 25th percentile for this distribution? And then what is another name for the 25th percentile? Okay, so now I'm going to change colors here. 25th percentile. So now I want to look at the y-axis. Okay, when I'm looking at percentile, I want to start on the y-axis, and I want to estimate where I think maybe 25% would be, and I want to come across until I see where it looks like that's going to intersect on the graph, and then I want to drop that down vertically to the x-axis, and it looks maybe roughly, that line kind of jumped a little bit to the left there. I'm going to call that $45,000 for the median household income for the 25th percentile. I'll just kind of make that a little bit wider there. Okay, so what this is saying is whatever states have a median household income of $45,000, that is higher than 25% of other states. Okay, their median household income is higher than 25% of other states here. Okay, so another name for the 25th percentile is what we would call Q1. That is called the first quartile. We learned about that when we did box and whisker plots, when we did that outlier test and find the interquartile range. There is a problem, I think, on your homework that asks you to take a cumulative relative frequency graph like this, and it's going to ask you to turn it into a relative frequency histogram. Kind of similar to how this came from this histogram here. Okay, and here's what I'll tell you need to keep in mind. You need to keep in mind that the steepest sections of your graph are going to create the tallest sections to your histogram. Okay, now this can get a little bit tricky, so I want to make sure that you're okay with this here. You'll notice I'm labeling the x-axis the same way that this is labeled here, and my y-axis is the relative frequency, which again is the percentages. Okay, now you might be wondering, why am I only going up to 30% when over here this is going up to 100%? Okay, keep in mind this one is accumulating as you go. I'm accumulating, so by the time I get over here to this very last state that roughly has a median income of 70,000, it's higher than almost 100% of everything else. Okay, so here's how this works. If you could follow this with me here. Okay, you're going to take this first bracket between 35 and 40. Okay, and you're going to look at that increase. It starts at 0, and it roughly looks like, I don't know, maybe it stops that 40,000 is maybe about 5%. Okay, that means 5% of the states have median incomes between 35,000 and 40,000. So when I come to my graph here, I'm going to go up to the 5% mark. I'm just going to go ahead and label 5% at the top of that. Okay, that's between 35,000 and 40,000. Okay, now here's where this gets tricky. Okay, I'm going to switch colors here. Now I want to look at between 40,000 and 45,000. Okay, now you'll notice where 45,000 ends, we said that was 25%. Okay, but 25% includes both of these sections combined together. I only want the growth from 40,000, which we were saying left off at 5%, up to where this stops at 25%. So this went from 5% to 25%. That's a growth of 20%. Okay, so I'm going to go up to 20% over. I'm just going to label at the top. Between 40,000 and 45,000, there were 20%. Okay, do you see how I'm doing this here? Let me do another section. Okay, let's do from 45,000 to 50,000. Okay, for this, now keep in mind, I stopped at 25%. This one here looks like maybe at 50,000, it stops at 50%. I just want the growth only for the section between 45,000 and 50,000. So if this is 25% and then this is 50%, from 25 to 50%, that's another 25%. So that means that section should be 25%. Notice how so far this bar is the tallest. Also, this section was the steepest. Okay, so that's what you do, is you just roughly estimate where you stopped, like where that segment starts, and where it stops, and you're only calculating the growth for that piece. So I'm going to go ahead and just fill in these other bars there since I talked through the first 3 with you. Okay, and I think these last ones are maybe all roughly about the same, 10%, 10%, 10%. Okay, that is how you change a cumulative relative frequency graph into a relative frequency histogram. That's why I didn't need to go up to 100%. Okay, because I was looking at each segment as its own separate bar on the graph. Okay, the last part to this question says, where is the original graph the steepest? And it kind of feels like the original graph it's pretty steep from 45 to 50 and from 50 to 55. So we're just going to call that all one piece here. And we're going to say it's probably steepest from 45,000 up to 55,000. Okay. And we want to know, what does this indicate about the distribution? Okay. Well, let's see here. From 45,000 to 55,000. Let's see how much is enclosed there. from 45 to 50. And it might even be easier, actually, for me to look here. From here to here, I'm including this much. I'm almost including half of the states, like roughly 45% of the states are included there, okay? Because if I combine these two percentages together. So I'm just going to say about half, roughly 45% of the states fall within this interval. Kind of feels like it's maybe 25th percentile to maybe 75th percentile, which that is known as the interquartile range. Okay, one other topic we're going to look at here on this notes page. Well, no, let's look at just a couple examples here that involve this idea. Okay, just to make sure that we are comfortable here with this. These are pretty quick and easy. We're going to look at this multiple choice question. It says, Mark receives a score report detailing his performance on a statewide test. On the math section, Mark earned a raw score of 39, which placed him in the 68th percentile. This means that, and we're going to decide which of these 5 statements do we think is the best description for saying that Mark's raw score of a 39 placed him in the 68th percentile. First, it says Mark did better than 39% of the students who took the test. Okay, I don't think that's what this raw score means. Mark did worse than 39% of the students who took the test. Okay, I think we're interested in this percentile here. Mark did better than about 68% of the students who took the test. Gee, that sounds pretty good here. I don't think he did worse than 68% of the students because 68% scored less than him. Mark got fewer than half the questions correct. Okay, the best explanation of the 68th percentile is C. Okay, let's look at number 2. Mrs. Munson is concerned about her daughter's height and weight and how they compare with those of other girls of the same age. She uses an online calculator to determine that her daughter is at the 87th percentile for her weight and the 67th percentile for her height. Explain to Mrs. Munson what this means. Okay, so we're going to go ahead and write this down here. This goes with number 2. Okay, if her daughter is in the 87th percentile, this means that her daughter is heavier than 87% of typical girls her age. Now, could you have said that a different way? Sure. You could have said 87% of typical girls her age weigh less than her. That's the exact same thing as saying that her daughter is heavier than 87% of typical girls her age. Either way is fine. Okay. Let's also interpret that her daughter is in the 67th percentile for height. We could say she is taller than 67% of typical girls her age. Okay, again, it would be acceptable to say 67% of typical girls her age are shorter than her. That would be completely fine. Okay, let's look at number 3 here. Okay, number 3 says, questions 3 and 4, we are to use this cumulative relative frequency graph here off to the side. It says it represents the length of phone calls made from the math department office at Gabolet High School last month. Okay, about what percent of the calls lasted less than 30 minutes? Okay, and then it says 30 minutes or more. Okay, so let's find the 30-minute mark here. I'm going to go ahead and draw a vertical line straight up here. Okay, see where it hits the graph. I'm going to come over here. Okay, that was kind of tilting down just a smidge here. Maybe I'm going to adjust that just slightly. Okay, so we're going to say for this first part here, let's say maybe about, and we're just going to estimate here, about 63% of calls lasted less than 30 minutes, and about, well, if 63% are lasting less than 30 minutes, then that must mean that 37% of calls lasted more than 30 minutes. Okay, and question number 4 says estimate the Q1, Q3, and then the interquartile range. Okay, so let me just go ahead and get rid of these here. Okay, Q1, that would be the 25th percentile. I want to estimate where 25% is there. I want to come down here. Okay, Q3 would be where 75% is. I want to estimate that. I want to come down here. Okay, so I'm going to say, now what I'm looking for here is I'm looking for, where these roughly are hitting down here. Okay, so I'm going to say for number 4 that maybe Q1 is, we'll call that 13. Okay, Q3, and this would be minutes. Okay, it's the call length. Q3 we'll say is 32 minutes, and then the interquartile range would be the difference in those, which would be 19 minutes. Okay. Okay, the last topic here before we stop here today is looking at transforming data. Okay, when we talk about transforming data, here's what we're referring to. Okay, this is when you're converting all the original observations that you have collected from their original units of measurement into some other scale. Okay, now when you do this, sometimes the transformations can affect the shape, the center, and the spread of your distribution. Okay, you can see here in this picture, here we have like a bar graph that's representing what the frequencies are of the heights of some high school students. Okay, these are in feet though. If we were to convert 5 feet into inches, that's where we're getting the 60 inches. 5.25 feet, we get 63 inches. You'll notice the frequency counts are the same. The thing that we're most interested in is if we were to say, what's the shape of this? And then after we converted those numbers, by the way, when we do that conversion to go from feet into inches, we would have multiplied every observation by 12. Okay, so we want to ask ourselves, did that change the shape at all? Well, gee, these two shapes of these graphs look exactly the same. And that's what we're going to see here, that the shape doesn't change when you alter the observations or convert the observations, whether you're multiplying all the pieces of data, dividing, whether you add a number to all of them or subtract a number. However, the center, if you were to estimate where the center of this would be, whether you're going to do the median, you're going to get a number, somewhere here, between 5.5 and maybe 5.75 feet. If you calculate the center here, it's a totally different number. It's between like 66 and 69 inches, okay? So it does feel like the center is a different number because we're in a different unit of measurement, okay? And we'll talk about the spread here as well, okay? So let's look at this example here. It says if you were to, and we're going to look at transformations regarding adding or subtracting a constant number to every single observation, okay? So if you were to add the exact same number, we're just going to call it A, to every single observation, here's what that's going to do. That is going to add A to your measures of center, which are mean, median, and measures of location, which are quartiles and percentiles. But what it doesn't do is it does not change the shape of the distribution, and it does not change any measures of spread, range, interquartile range, or standard deviation. Okay, here is an example to kind of illustrate this for you. Okay, what we have here is we have 2 dot plots. Okay, 44 students were asked to just eyeball and guess what they thought the width of their classroom was. Okay. And so the guess was in, I think they guessed in meters, okay? Their guess was in meters, okay? So this bottom dot plot here represents all the students' guesses, and this bar right here represents all that data, the range, interquartile range. Here's the 5-number summary, standard deviation mean, and 44 students, the number in the sample, okay? Now, what happened was, when the students, okay, before we get into that here, we're going to describe the shape of this guess dot plot, okay? We're looking at this one right here right now, okay? So as we describe this here, and we're going to go ahead and do the shape and the center and the spread, it kind of feels like maybe this is centered, and I'm just looking at the right here, what they're giving us. Since the shape of this is somewhat skewed right, I'm going to say the shape is skewed right. And because it's skewed, it's better for me to describe the center by using the median than it is the mean. Because if I've got some outliers or potential outliers here, I want to kind of steer away from the mean and stay closer to using the median. So I'm going to say it's centered around 15 meters, and I'm going to choose the measure of spread to be the interquartile range instead of the standard deviation, again because this is skewed, and the interquartile range is 6 meters. Okay, that's of the guess dot plot. Now here it says the actual width of the classroom was 13 meters. Okay, that was the actual width. The guessing error is found. So how far off were you? Well, if you subtract 13 from your guess, that tells you how far off you were. Okay, so the error dot plot, now we're looking at this top dot plot here, that represents how much each student's guess was actually off by. Okay, and how we got this is this was created by taking each student's guess and subtracting 13 from it. Okay, subtracting 13 from it. So now we're going to look at this. Okay, and we're going to describe the mean median mode here. I want you to, not mode, the center and the shape and the spread. Here, one thing that you'll notice is how the shape is the same. So I'm going to make a note here. Shape doesn't change. Okay, the shape doesn't change when we subtracted a number from every single observation. However, the measures of center and measures of location, those are going to change with addition and with subtraction. Look at how it changed. Look at what the error was. See how it dropped? The center dropped by 13. So it went down by 13. The measures of spread, range, interquartile range, standard deviation, okay, you'll notice those, we can even compare from here to here, okay, those did not change. Okay, so measures of spread don't change with addition and subtraction. Okay, it stays the same. Okay, stays exactly the same. Okay, finally here, if you were to take a set of data and you were to transform it, instead of by either adding or subtracting the same value from every observation, you either multiply or divide each observation by the same number. What this will do is it will change the measures of center, but now it will also change the measures of spread. However, the shape will not change. Okay? And you can see that here with, if we were to take the error dot plot and we were to convert it from meters into feet. Okay, if you change from meters into feet, that means you multiply all of the measurements by 0.3048. Okay, you'll notice the shape still skewed to the right. Okay, so we're going to say, guess what? The shape didn't change. Okay, shape didn't change. However, let's look at mean, median, quartiles, range, interquartile range, and standard deviation. Okay, to go from, we'll just use the mean here, to go from this number down to this number, or the standard deviation, that's a spread, down to that number. Okay, I kind of highlighted over top of it there. All right, they all got multiplied by 0.3048. Okay. All right, this is a good place for us to stop here with this. These are some problems that you can go ahead and try here that go along with these problems. We'll pick up from